What's up guys, it is Mike the Space Science Guy. There's been a lot of press lately about asteroid mining companies such as Planetary Resources and Deep Space Industries. Basically these companies want to get to asteroids and either return them to Earth or develop the resources and extract them from the asteroid and bring those back to Earth. Some of these asteroids are estimated to be worth up to trillions of dollars in terms of iron, nickel, platinum group metals, other elements that can be brought back to Earth and used on Earth. But in fact, one of the other valuable resources that asteroids have to offer is ice, water. And why ice, you might ask? Well, basically water can be broken down into hydrogen and oxygen using electrolysis, and this can then be used as a fuel in space. So the hydrogen can be burnt using the oxygen as an oxidizer. So if you bring this ice into orbit around Earth, you can use solar panels to get electricity and then use that to electrolyze the water, break it down to hydrogen and oxygen, and then you've got a fuel that you can use in space, either in orbit or for missions leaving from Earth's orbit. So in actual fact, it costs over $3,000 US to get 1 kilogram of material from Earth into low Earth orbit. The reason for that is the fuel costs to get such a small amount of material into space are extraordinary. So if you've got this fuel that you can take from space and then use it in space, you're saving yourself $3,000 per kilogram of material. So you can sell this ice water now, once you've broken it down into hydrogen and oxygen, you can sell that for $3,000 per kilo, which is extraordinarily valuable, much more valuable than it would otherwise be if you just brought it back to Earth and sold it as water. It'd be hardly worth anything. So that significantly boosts the economics. And it turns out there's actually already a big market for fuel in space. Satellites, for example. So at the moment there's over 350 communication satellites in geostationary orbit around Earth, which means they're constantly above the same position on Earth. They rotate with the Earth. And at the moment these satellites basically die when they run out of fuel, which they need to maintain their orbit. So a company, ATK, has proposed a tug, basically, that will keep these satellites in orbit for a service of about $25 million per year. So there's 350 geostationary satellites at a market of $25 million per year, let alone all the other satellites that currently exist, let alone, again, the satellites that will exist in the future in other space missions that will be leaving from Earth's orbit. This is a multi-billion-dollar market, so that when you take into account the possibility of bringing ice back to Earth, that significantly improves the potential economics of asteroid mining. But there's just one problem with all this. It turns out it's actually really hard to work out what an asteroid looks like on the inside. So there's been a few missions now that have landed on asteroids. These have provided a little bit of extra information about the surface. We do have a lot of photometric, hyperspectral imagery, and other light-based data from asteroids. We've got some information about their gravity, their magnetics, fields, but none of this really gives us a detailed look at what the asteroids look like just a few meters or even a few centimeters below the surface. We've also got meteorites that we can pick up on Earth, and it is possible to relate these meteorites to existing asteroids or families of asteroids and try and use that to infer what these asteroids might look like on the inside. But that tells us something about the composition, but not necessarily about the structural shape and type of an asteroid, which would actually significantly impact not only mining techniques that you might use, but also whether or not there's pore space that ice can be trapped in and things like that. There's a lot of different structural models for asteroids, which range from anything from a solid rock, a rock with some fractures and pore space, kind of like a Swiss cheese on the inside, or a rubble pile or a gravel pile, which is just loosely held together by gravity and electrostatic forces, or even a solid body with just a layer of soil or regolith on the surface. And each of these have their own implications for mining and the value of the resource that are available. We speculate that some of the larger asteroids, like Ceres, the largest asteroid in the main asteroid belt, possess layers like the Earth does, but some of the smaller asteroids we aren't really sure. And that again would have implications for mining. If the surface is highly rich in some metal, and we go and develop that asteroid for metal, assuming it's the same the whole way through, only we get below 2 meters, and then suddenly it turns out the rest of it is just some silicious rock that's not very useful. That's blown our whole economics out of the water, and the mission will probably be a failure. So it's important to try and work out what asteroids actually look like on the inside. There's a couple of ways to do this. Some researchers, myself included, are looking at ways to do this, including using seismic techniques. So seismology is used on Earth for it's the measuring the propagation of sound waves through some part of the Earth, and it's used for looking at earthquakes and learning about where they originate from, their magnitude, but also it's used a lot in resource exploration, especially oil and gas exploration. It's used to look at the structure of the Earth where oil and gas might be trapped. Some researchers have proposed dropping sound receivers onto the surface of an asteroid, so they measure the vibrations on the asteroid, and then firing some kind of slug or bullet into the asteroid to induce vibrations throughout. And then if you know the precise location of where that slug hit the asteroid and the location of your receivers across the asteroid, you can measure the reflections and work out what that tells you about the structure of the asteroid. So if there's fractures or things like that where ice might be trapped, or where there's other types of different rock layers. Other methods include using ground-penetrating radar or radiotomography, which involve using light waves of different wavelengths, which then bounce off different layers of rock within the asteroid, and then you can get return signals similar to your sound waves to work out the structure of the asteroid. Of course, one of the best methods, and this is what we call ground truthing in the geoscience industry, would be to actually drill a hole into this asteroid. So you can test your different models and your other geophysical methods, like seismic and ground-penetrating radar, to actually physically see what the rocks look like there. And so you're not just inferring based off of other data, you've got a physical sample. Unfortunately, that's expensive on Earth, let alone doing that on an asteroid. So ideally, for exploration, we'd want something that we can do cheaply for a lot of asteroids, and then maybe once we've picked a few key targets, we can then go ahead and start drilling some holes in advance of mining these asteroids. Anyway, hope you guys enjoyed that quick introduction to asteroid mining and exploration. As always, if you want to know more about my research, you can click on my website on the link below for my blog and some of my work. Or if you like my video, please click subscribe. And if you have any questions for me, feel free to leave something in the comments below. Thanks for watching. Until next time.